Okay, let's assume it's basic 1, 0, 0, 0. So using this definition, what would be this? So this would be x of 1 partial by partial xi. Okay. And what would be x of 1? So it depends on what is x actually. Okay, it depends on what is x. But whatever x is, since it involves partial x and partial y and partial z, this would be 0. You're going to get 0 here. So I can say that 0 is a 0, E1 plus 0, E2 plus 0, E3. Okay. So in other words, if you compute the connection forms for, Euclidean space actually, okay, or the basis vectors, you're going to get 0, 0, 0, 0, null matrix, because all of the components are going to vanish. But that's true in Euclidean sense. This is not true when these EIs are not Euclidean. For example, if they are polar or they are spherical, this is not necessary. Okay? For example, if I take EIs to be, so that's if I take this R, phi and theta and phi, for example, spherical coordinates. Okay, and I want to compute the connection forms for it. How does it going to look like? First of all, what would be the transformation matrix? In other words, what is the matrix that takes me from here or maybe Ex, Ey, Ez to Er, E theta, E phi. How can I compute this matrix actually? What would be this matrix? So the first would be partial x by partial r, okay, and partial y by partial r and partial z by partial r, partial y, partial x by partial theta, partial y by and partial z by partial theta, and partial x by partial z, partial r, partial z by partial x by partial phi, okay, partial y by partial phi and partial z by partial phi. And it turns out if you compute this matrix, okay, you're going to get one matrix actually, okay, and this matrix is, okay, sine theta cos phi, just quickly writing it, and sine theta sine phi and cos theta, and you have or cos theta cos phi or cos theta sine phi and minus r sine theta, okay, and the last would be minus r sine theta sine phi and r sine theta, okay, what? Cos phi and 0. Is it making sense? So this will be the transformation matrix. Now, so what I'm just doing is that I want to show you that if you computed the connections form with respect to the Euclidean basis, they all are vanishing actually. But this is not true for all the coordinates. I'm going to show that basically that if you take basically any other curvilinear coordinates, they're going to survive actually, some components are going to survive. For example, what would be ER in the terms of, so what is this? This is telling you actually. So if I write this in equation form, what does it mean? That ER is equal to this multiplied by this actually. Okay? So this would be sine theta cos phi EX plus sine theta EY plus
cos
theta EZ. Okay? And I would like to write just one more expression, that is, okay, E theta. So E theta would be
or cos
theta cos phi Ex plus or cos theta sin phi Ey plus minus r sin theta Ez. Okay? Now here's the thing. What would be partial ER by partial R? It must be 0. There isn't any R. Okay? By the way, what would be partial ER by partial, for example, theta? Okay? You can verify that this would be E theta 1 over R. E theta by R actually. So you're going to get the same expression as E theta divided by R. So you're going to get this. Are you getting the point? So now you can see that if I differentiate, you know, if I do this, for example, okay, so if I take E1, which is 1, 0, 0, 0, and I differentiate E1 with respect to X actually, I'm going to get 0. With respect to Y, 0, with respect to Z, 0. Similarly, E2, E3, E, you know. But in case of the, you know, what do you call, these coordinates, it's not going away. It's not going away. Are you getting the point? In other words, if I have to, now you can realize it. In other words, if I have you know, the covariant derivative of ER, and I want to compute it in the direction of some vector, okay, this is not necessarily 0. So you're going to get some coefficients as a result here. Okay, you can compute it basically. You're going to get W11 of XER, W21 of X E theta plus W22 of X EZ actually. You can compute it. Okay, how can I compute this? This depends on the definition actually. What is the definition? Here. So for this I need to know what? I need to know these coefficients. So if I want to apply this, so how does it going to, what would be the output? Output would be X operated onto, but I have to also express X in the terms of polar coordinates, okay, and then apply ER, and then, you know, maybe EI, but EI means ER, E theta, E phi here, and compute partial by partial X sign. In other words, now it's not necessary that this would vanish, these coefficients. These directions, they can survive. Are you getting the point? So in Euclidean coefficients, these all survive. But in curvilinear coordinates, they all vanish actually in case of Euclidean, but in curvilinear coordinates, they can survive. We're going to move ahead tomorrow. I'll be the next speaker.